Hello and welcome to this lecture on MRI the Basics, Chapter 11. It's all about image construction, Part 2, which is spatial encoding. And it's our distraction for the day here. There it goes. So this is an interesting technique called amplified MRI, where basically they took microscopic or very small scale motions you can measure in the brain, like happening with pulsation. And actually, I'll start that again. We actually amplify these motions in the image, and so you get this like much more expressive, amplified picture of the brain motion during an MRI scan. So, pretty interesting approach here. Okay, really, we have a pretty clear goal, but this is a big goal for this lecture, which is to understand the essential concepts of what we call 2D FT imaging. So this is both frequency and phase encoding. And then briefly, just sampling from the respective how do we store this data that we've collected for spatial encoding. So starting off with an overview of how are we going to create an image. First, we're going to perform some sort of slice selection with our RF pulses, as we discussed in the last chapter. Then we're going to move on to this, the spatial encoding piece, which for 2D case, the most common way this is done is with 2D Fourier transform or 2D FT imaging. The reason for this name will become more clear as we continue to use this technique. It has two parts of it, the frequency encoding, sometimes I'll abbreviate that as FE. This is gradients applied during our data acquisition and results in one dimension of a resolved image. And then the other dimension we do phase encoding or PE. And here, as we'll see, we'll change the gradients between our TRs, and this resolves our second dimension to create a two-dimensional image. This is not the only way to create an image. There's back projection reconstruction or back projection methods that we'll also cover briefly here. Spiral imaging, that is an advanced topic we won't cover, and echoplanar imaging, which we will get to in chapter 22. Okay, and I also want to start here with a refresher on what leads to MRI signal, because we're going to use this looking at the net transverse magnetization in the course of this lecture. So if you recall, it's the precession, the resonance frequency of the transverse magnetization, MXY, that creates this changing magnetic field and induces current into our RF coils. And recall, again, that all the signal is only coming from MXY, the transverse magnetization. And our RF coils are going to get this lumped measurement of the transverse magnetization. So it's kind of what's illustrated in the picture in the bottom here, is that we have these large centimeter, multiple centimeter size RF coils, and the signal we get is the sum of the transverse magnetizations from that entire RF coil. An RF coil does give us some amount of localization. It's very coarse, like on the scale of centimeters, but nothing nearly like the millimeter scale that we're going to want from MRI. So here's the picture that I showed earlier in the chapter 2 lecture of gradient encoding. And basically, this picture that I've shown here is the first way that we're going to distinguish signals from different parts of the body to do spatial encoding. And that's where we're going to do so-called frequency encoding. This example, normally just have our main magnetic field B naught. All this magnetization is rotating at the same resonance frequency. We turn on magnetic field gradient, which leads to this relationship here between the main resonance frequency and position. And now I have this linear relationship, this gradient across position of the magnetic field, which leads to a change in resonance frequency as a function of position. And then if we look at the transverse magnetization at two different locations, we'll see they're going to precess at two different frequencies. And this is what is going to allow us to distinguish these two different locations. And this is basically the premise of frequency encoding. And just to show it again in a different direction here, if we apply the gradient in the x direction, we look at net magnetizations from two different locations. In x, again, we see the same phenomenon where the magnetic field gradient creates these differences in resonance frequency as a function of position. And what frequency is going to do is create an image by separating the signals at these different frequencies. So if we go into our diagram of our pulse sequence, I'm going to play an excitation pulse, in this example a 90-degree excitation pulse. And after that, we're going to turn on the magnetic field gradient, in this case Gx. And what that's going to create is, again, what we've seen in the previous pictures. Let's just formalize it here. It is going to create this relationship between frequency and position. Gx here is chosen because conventionally we denote Gx as the frequency encoding dimension. And we have this relationship here where the frequency is going to be gamma bar and times the main magnetic field plus Gx naught, so whatever the amplitude of this gradient is, times the position in x, where Gx naught would be the height of this gradient that we've turned on. And then we're going to be acquiring data while we turn on this magnetic field gradient to separate our different resonance frequency locations. So you can imagine if we have some net magnetization at some position out here, it's going to have one given frequency during our readout. However, if we have another part of our subject or some net magnetization somewhere else in position, this x dimension, it's going to resonate at a different frequency. And I'm going to go through this for this simple object example. It's also used in Chapter 9, discussion of the Fourier transform. So here's that simple object where we do no encoding, so we have no gradient turned on, looking at the lab frame, where this simple object at these three positions has different transverse magnetization at each position, and our MRI coils are receiving the signal from all of these different positions. So we're going to get a signal that is a mixture of these three positions, but in the case of no encoding, they're all going to be resonating at omega naught here, the same frequency. So if we take the Fourier transform of the signal, there's only one frequency present in these different curves here. So you're going to get an image where all these parts of the simple object are stacked up at the same location. We're basically not going to get any sort of image in this case. Now I want to move us over to the rotating frame, because that makes our analysis a bit easier, in which case we remove the omega naught part of the oscillation, which just leaves us with what would be a constant signal amplitude over time. which you can use the Fourier transform pair that's used to derive this, is that if our function here in t is just a constant, say 1, the Fourier transform of that is going to be this delta function. So this function that exists only at a single point, at the 0 point here in the frequency space without this encoding. And just putting that together, again, we don't receive these different, we can't separate these different blue, red, and green curves in the signal. In fact, we only get one signal value, so it's just going to be this constant amplitude signal. And just a reconstruct would basically be a single pixel of an image here. So if we add frequency encoding to this picture, we showed a few slides ago where we have this transverse magnetization created by some RF pulses. We turn on a magnetic field gradient, so we get this relationship of frequency versus position. Now, each of these separate positions in this simple object is going to have a different resonance frequency because they're at different positions. So, for example, our red object here is near the center or near the isocenter. So it has a very low frequency in the rotating frame, whereas the green and the blue components are much further away from the center, so they have very much higher resonance frequencies. And you can here the solid and the dashed lines are plotting the real and imaginary component because these are complex exponentials of some form like this. They have a real and imaginary component, and we actually have a concept of positive negative frequency in here, and that has to do with the difference in the real and in the imaginary component, in fact, of the sinusoids. Okay, so this is a good situation now. We've got frequency encoding happening here. We have different frequencies in our signal, and this is what our actual signal would look like. Our signal is not the individual curves that I showed on the last slide. It's the sum of those. That's what our RF coil receives. It's the sum from all of these different positions. And this is where we need the Fourier transform to disentangle or to resolve these different locations, which are based on the different frequencies in this signal. Okay, so what this signal here is it's the sum of 3 sinusoids at different frequencies with different amplitudes. We could write that mathematically like so. And when we take the Fourier transform of that, we get, and I'll just do a shorthand here, delta, the sum over our different I, so these different components of a scaled and shifted delta function, which is basically these, in the image is these 3 separate objects. Okay, so here we've got frequency encoding. This is the basis of this. We can look at this in the net magnetization space, and this is just another way of looking at it. It becomes tricky to look at frequency and phase encoding in the net magnetization space. That's why later on we'll begin to introduce the concept of K-space, which is a convenient and more efficient way of representing the effect of magnetic field gradients. But just let's step back and look at the net magnetizations here. And this very simple example first, right, where we've tipped transverse magnetization now across our subject here. You know, this could be transverse magnetizations within our subject. And recall that the signal here is proportional to the sum of all of these different transverse magnetizations. And this is shown in the looking here over time after an RF pulse. And without T2 decay in the rotating frame, nothing changes here. Now when we add a magnetic field gradient, and this time I've added it in the y direction, because by convention we usually use GX for frequency encoding, but physically we can move it between any different direction that we want. And so what happens now is that you can see over time here, so this first picture here corresponds to just after the RF pulse, again when all the net magnetization transverse magnetizations, are pointing in the same direction. Then we proceed some amount of time, and our net magnetizations are rotating, and they're rotating in different amounts at different positions because they have different frequencies. We can come to the further along in our gradients, they continue to rotate. This top row up here is rotating this way. That's high frequency. As we get closer to the center here, it's rotating at lower frequencies. And then the negative frequency, in fact, means rotating in the opposite direction. So have rotation in the opposite direction as we get to the other side of the center, what's called the isocenter here. And so we have a range of low versus high frequencies. In fact, usually this would be a high positive frequency down here, and this up here would be a high negative frequency. And then when we look at the signal we would get from this object, now unlike the previous slide where it was simply a constant, the added gradient there now strongly modulates this signal. And so you can see these net magnetizations begin to add up incoherently. They can even cancel out at certain points in time. And this is a dummy example for a uniform object. And this is going to change depending on what the size of these transverse magnetizations are. But just here to illustrate what's going on with the net magnetization, and again refreshing that we have to consider the sum of the transverse magnetizations as to what is contributing to our signals. So I want to go through this example here where what the goal is going to be is I've got 3 different configurations of a 2D object here. And I want to figure out how we can distinguish these 3 different possible configurations of the object. And if we just apply this x gradient with some, say, amplitude Gx0, that means in our signal we're going to have a frequency it's going to depend on, let's just do it in the rotating frame here. So take out the b naught term, but gx naught times x. Okay, and what you can see in all these objects is there's two positions in x. And I'm just going to draw these as the real part just for simplicity in this example. But in reality, it's a complex exponential. So what's going to happen is, since the red, the yellow, and the blue object are all at the same location in x, their contribution to the signal is all going to be the same. I'll do my best to kind of draw the same frequencies across here. And similarly, for the orange, the green, and the purple object, they're going to be at some further location, so they're going to be contributing some higher frequency. And so in this case, actually, we cannot distinguish which of these three objects we're imaging here. And I'm color coding them, but really these colors are just to show you correspondence between the components of the signal and the object. But if we took the Fourier transform of this, we get the same looking spectrum, which in our case is going to be the same looking object for our image, no matter which of these three possible objects could have actually been in the magnet. So how are we going to resolve this? We need to go from the 1D frequency encoding to some sort of 2D imaging to distinguish these different types of objects. So actually, one of the first ways this was tried and done, we're going to build up what's called the back projection technique, where you can say, well, okay, let's just play a gradient on a different axis. Say here, gy, give it some amplitude gy naught, and now our frequency is going to change as a function of y position. So in the first case, these two objects are at the same y location. So they're going to have the same frequency. And when we reconstruct, when you take the Fourier transform here, actually they're going to be stacked on top of each other at the same point in our spectrum. So they're going to show up as one single peak there. But the other two objects here will show up differently. So the green object has a high frequency because it's further away in y, whereas the yellow object here is closer to the center in y, so it's going to have a lower frequency, show up at that lower frequency in the Fourier transform. And in this case, the blue, oh, my drawings are getting worse as it goes along here, the blue object will show up at the higher frequency location, the purple object, I'm even getting the axis, the intercept wrong here, it's going to show up at a different location. Okay, so now we've done a step better. Now we can at least distinguish configuration 1, the top row, from the other two. Okay, so we now have resolved, if we could resolve, again, this top configuration of these two objects from the bottom two configurations of these two objects by switching our frequency encoding from X to Y. However, we cannot distinguish the bottom two configurations of that object. So to do this, we do combine turning on of both of the magnetic field gradients. So we might turn on, just say for the sake of argument here, we'll turn them on to the same values we had before, in which case now the frequency depends on both X and Y. Okay, so it sort of depends on basically a distance at some other angle. What that can mean is that there'll be some line here that corresponds to, or can look at the opposite way, there'll be some line here that corresponds to a frequency equal to 0, where there's no shift. And then how far the points are away in this opposite direction is actually going to determine. So again, this is a line for that equation being solved to be equal to 0. And then how far these points in our object are away from that line is going to determine their resonance frequency. So it's getting a little more subtle here. But in this case, the red have a slightly lower frequency, and I'm drawing these a little compressed in the center in this example here. The red will have a slightly lower frequency. The orange will have a slightly higher frequency. Now, because of this configuration, the yellow is actually quite close to the F0 line, so it's going to have one of the lowest frequencies of this configuration, so it's going to show up way over here. The green, conversely, is one of the points that's farthest away from this frequency equals 0 line, so it's going to show up out here. And then actually in this case, the blue is equivalent to the red above, and whereas the purple is only very slightly higher frequency than that. But now we can see in this case, we're able to distinguish between the configurations of the second and the third row here, where before, either with just the X gradient, we could not distinguish any of the configurations. With just the Y gradient, we could distinguish the first configuration from the second two. And now with this gradient on in two directions, we can start to distinguish the second and the third configuration. And you can think of this as basically a simple version of what the imaging problem is. The imaging problem is basically to differentiate different locations or different configurations of sources of signal. So there's a name for this technique that we're actually building up of both applying X gradient, frequency encoding, Y gradient, frequency encoding, and maybe some mix of the two. And this is called back projection, also known as projection reconstruction, or sometimes called radial imaging. And it turns out to be mathematically very analogous to your tomographic imaging modalities, CT and PET. And where basically what you're going to do is do what is effectively a rotation of this frequency versus position relationship. So in all these plots here, the gradient is going in one direction, and this line going this way is the line where the frequency, all frequencies are equal to 0, and so on. Okay, and so we're rotating, effectively rotating this relationship of frequency versus position in 2 dimensions. And then you can use the back projection type reconstruction or some other reconstructions to create an image. This is an interesting approach. It was actually one of the original methods proposed and used for MRI acquisition. So the image up here, the first ever human head image using MRI, and they did use a back projection type acquisition scheme. However, in modern MRI, it's actually not very common. It's quite a small fraction of MRI that's done, primarily used for some to solve some very specific problems, particularly motion correction. And you'll find these under the names of the grasp or the propeller techniques. So why don't we do more back projection MRI? Putting things simply, it's sensitive to the effects of off resonance. So if the magnetic field isn't exactly what we think it is, or there's magnetic susceptibility differences or chemical shift, the images tend to degrade less gracefully than the next technique we'll cover, and it's very sensitive to the gradient fidelity. So when I draw the magnetic field gradients, we assume that they do what we think they're going to do, but that's not always the case. Now, the reasons to continue to do back projection or similar MRI methods is they are inherently less sensitive to motion, and they can actually include motion navigators in them because of the way they sample data. And it turns out they can also start the data acquisition very, very quickly. So how really do we do 2D imaging? And the more common way to do 2D imaging is to take frequency encoding in 1 dimension, and in both sequences it's conventionally written along the x dimension, and to do the process we're going to go into next called phase encoding on the 2nd dimension to create image resolution or spatial localization in that dimension. Let's start by examining the concept of phase encoding by looking at the transverse magnetization. And this is where the term phase encoding comes from. Where if you recall, the phase is going to be defined as an angle here of rotation of our transverse magnetization. And in this initial illustration here, this is for no gradients turned on. So there will be, in fact, no phase accumulation over time, or there's no change in the phase as a function of position. But what coding is adding a small gradient, so we're turning the gradient coil on and then off, which creates a net rotation. It creates some phase angle as a function of position here. So while the gradient's on, we get rotation by either low or high frequencies. When the gradient is turned off, then the rotation stops and we have some fixed phase pattern that we've created like this. So again, showing this over here in time, it's going to start after excitation with no phase change as a function of y. I'm going to turn the gradient on, which is going to cause some rotation, so there's going to be some phase that accumulates as a function of the y position. And then as soon as we turn the gradient off, this phase does not change anymore. So this phase that is due to the magnetic field gradients is fixed. And illustrating that over here, we have phase that is some function of the position y. And so this would be what we call one phase encoding step. And then what we do next is actually change the amplitude of this phase encoding gradient. So now we've created an even further rotation or a larger phase angle. Again, the rate of rotation here is in this high frequency at the edges in y, lower frequencies toward the center of y, but we increased the magnetic field gradient, which has the effect of increasing the amount of phase accumulation. So there's more frequency across the same range. Maybe I should draw that as big arrow compared to the last slide here. So we have sort of very high frequencies at the edge of our y dimension here. So we get a lot more phase accumulation with the larger y phase encoding gradient in this case. But then after we turn this gradient off, the phase remains fixed. It's unchanged. We're going to illustrate that in this picture. I have to draw a much higher slope, so a greater phase accumulation as a function of y. And we'll even do switch the gradient around, so now we have a rate of rotation going opposite as the case before, or the phase angles that we create will come in the opposite direction. So that's going to look like our phase as a function of position. It's going to be inverted, or in this the slope of this phase over time, it's going to be negative. And so this is the basic idea of phase encoding. It's that we're doing these different phase encoding steps. We're stepping through different combinations of this phase pattern as a function of y through the application of these short magnetic field gradient pulses on the y-axis, or on our phase encoding gradient axis. And now if we try to add in together both frequency and phase encoding, it becomes very difficult for me to draw this. So I created this little animation here showing what's going to happen, and let's let this run a few times. What you see at the beginning here is we create this rotation as a function of y. So the up-down direction in this plot is the only direction there's any variation. And then after that is when we're going to turn on this frequency encoding gradient, and you see we get sort of this mixture of different patterns of the net magnetizations during these different phase encoding steps in y. And the fact that this looks different, each one of these steps, is in fact what helps us fully resolve our image. Okay, so we're going to go back to this example of sort of a simple imaging problem where we want to distinguish these three different configurations of these 2-point objects. And I'm going to start off here just looking at, again, as we did before, just having a frequency encoding gradient on. Although the one thing that's going to be different is there's a gap between the excitation and the frequency encoding gradient. So there's a gap between when this frequency encoding begins to happen. And so the way that's going to be drawn in this signal here is that initially there's no gradient on, so there's no change in the signal, no frequency. And then once we hit the gradient here, we'll get some oscillation. Okay, so the red object here, the Fourier transform would appear on one side. And now I'm also going to pay attention to the phase in the Fourier transform, which basically corresponds to this initial value of the sinusoid. And we're going to define this one to be this case to be starting at that amplitude to be a phase of 0. And we're going to see for the other point source in this object, and it's further away in x, so it has a higher resonance frequency, but it starts at the same amplitude here, so it has the same phase. So the phase of our sinusoids is related to like the starting amplitude. And that's going to become important when we add in the phase encoding gradients. And if you recall, in this case, we're actually not able to distinguish any of these three objects. Even though I've added in the phase here, that doesn't help us until we get our phase encoding gradients. So initially we get some signal, but there's no change in the resonance frequencies and with no gradient. As soon as the gradient is turned on, we'll get some oscillation or change in the frequency that shows up in our Fourier transform. And our two different objects have two different resonance frequencies. But again, we can't distinguish between these three possible configurations. Next, we are going to add in this phase encoding gradient. So what is this going to do? So we're still going to have during our frequency encoding gradient, so at this time interval here, we'll have this frequency of gamma bar, gx naught, an amplitude of gx naught times x. But we can also figure out what the phase angle that we're going to get from gy is if we know what the time of this pulse is and the amplitude. Because how far it rotates depends on the frequency and the time. So another way of putting that is the phase. Phase generally is simply 2 pi times the frequency times the time. So if we want to look at, let's call this phi y, or phase in y, after this pulse, then this is going to be 2 pi gamma bar gy0. So that's the frequency, and then y, which is the frequency during this time interval. It's same equation that we had for frequency encoding. And then the phase is allowed to accumulate for some time, tau y here. So let me start illustrating that before getting too caught up in this equation. Okay, so we're going to start again with our signal or our transverse magnetization for this red object, having some value here. But now when the y gradient is turned on, since the red object has some net distance in y, it's going to begin to oscillate due to the y phase encoding gradient. It's going to stop at this value here once that's turned off. And then, since it also has some offset in the x direction, when the x gradient is turned on, it has some change in frequency. Now it's going to be a slower change in frequency again, just like our prior examples. And then when we're taking the Fourier transform here, we're taking it of this portion of the signal here. So we still have this red object would still produce a low frequency component. Okay, but now this initial amplitude here is offset, and this is what corresponds to the phase. So we're going to have some non-zero phase value here that'll just indicate by this line. Okay, let's go through this for the orange object. Since the orange object is at the same displacement in y, it experiences the same phase accumulation, the same phase offset during the phase encoding gradient. But now it's much farther away in x. So again, as in the previous pictures, it's going to have a higher frequency oscillation during the frequency, this x gradient. So when we take the Fourier transform, it has a higher frequency, but it also has the same phase offset because it has the same y position. So basically these values here are corresponding to, these are proportional to the y position. And then, so this is the phase encoding. We've encoded y in the phase information when we take the Fourier transform. And the distance along the frequency axis here is corresponding to x position. So let's continue the illustration and reinforce this. So now we have some differential location in y. So this yellow object is only a very small offset in the y direction. So in this first interval, it's going to rotate more slowly, as we saw in the previous pictures. So it might rotate more slowly during this interval. And then it's also at the lower position in x. So it's going to have this slower rate of oscillation in x. So it's going to end up at this lower frequency in the Fourier transform. So this signal has a lower frequency. And then the phase it accumulated, this corresponds to this offset here, is going to be less. Excuse me. Come on, pen. So if I've drawn that correctly, the phase accumulation when we start the acquisition is smaller than it was for the first configuration, excuse me, of the red and the orange. And this is going to become more obvious when you compare it to the green here, which has a higher offset in y. So it's the same as the red and the orange object, so it's going to have this large phase accumulation during the phase encoding gradient. And then it also has a high offset in x, so it's going to be it looks identical to, in fact, to the orange object above. It has this high frequency component, and it also has this higher phase offset. So now in the phase of this signal, we have a difference here in the phase that is beginning to provide information about what's happening in the second dimension. And let's run through this third example as well, where now things are first mixed up as they should be. We have a high offset in the y dimension, so we're going to get a large initial phase accumulation during the phase encoding, and then a small offset in x, so we'll get low frequency during frequency encoding. So end up at the low frequency, but with a high phase offset. And the purple object has this low phase accumulation, but a high frequency. So the purple object, would show up at the high frequency, but with a lower amount of phase accumulation. So this is another way of thinking about where this concept of frequency and phase encoding comes from, is that if we look at our received signal and we take the Fourier transform of that, or we think of the sinusoids, the frequency of the sinusoids, so which is going to show up in our Fourier transform, corresponds to the x position, and then the phase of these sinusoids is going to correspond to the y position. So the phase being the initial starting point of these sinusoids, which will also show up in the Fourier transform because we have a complex valued output there. And if we go to an example here of an even larger phase encoding gradient, now we might get something like even more phase accumulation for these higher y offsets, followed by low frequency, low location in x. So again, we're still at this, the frequency encoding, so the position of these peaks in frequency doesn't change, but actually we may be back here to where we've gone. Remember that phase is cyclic, so we can go all the way around 2 pi phase. And we'd see the same type of accumulation for this orange object, but it's at the higher location, higher frequency. And we could actually be back at a point here where the signal looks identical to the way it did with no y phase encoding gradient. Let's see if we can distinguish our other objects here. Now our yellow object is closer to the origin in y, so it has less phase accumulation. It's low, not very far in x, so it has low frequency over here. So it's going to have a higher accumulation of phase than it did before. In the previous example, and compared to the green position here, which maybe, let's say it's a full 2 pi cycle of phase, it has high frequency, it might appear like this. And then if we go through the final example here, we have blue gets its large amount of phase accumulation during the phase encoding gradient, and low frequency, but it's got this high, so 2 pi phase accumulation, whereas the purple location has sort of intermediate amount of phase accumulation at the high frequency. Okay, so again, what we're doing is there's some encoding of y in the phase, and then we still have encoding of x in the frequency dimension here. So what we have to do to actually create an image is we're going to have to repeat our pulse sequence. And now here I'm showing a full 2D pulse sequence with a slice selection gradient. So that's Z here, SS, slice selection. We have a frequency encoding gradient on GX. We have a phase encoding gradient on GY. And then what we're going to do is repeat this sequence. So we know the repetition time, TR, is defined there. And what we end up doing is have to step through these different phase encoding amplitudes in order to fully encode our second dimension. Because as you see, we can get to points where there's we might have some redundancy because of this cyclic nature of the phase encoding dimensions. So it turns out we've got to do multiple phase encoding steps to fully resolve an image. And I'm going to illustrate here how this we end up storing this in what's called our 2D matrix, which is going to be our K-space data, which will continue to define what K-space is in the coming chapters. And so basically the idea is that, say in the first TR, we would play this phase encoding gradient and then acquire some data, and that would end up being the high phase encoding gradient amplitude, so it'll be stored in our data matrix in this row. Then next, I do a lower phase encoding gradient amplitude, so that would be stored with a smaller, as it says here, towards the decreasing gradient, or importantly, we can define, let's say we could acquire the data with no phase encoding gradient for 1 TR. That's going to be put in the central line of our K-space here. And then let's just say eventually get down here to doing a large negative phase encoding gradient, and that's going to fill out one other edge of our 2D data matrix, which is our K-space. We'll continue to look at the concept of K-space and build this up over the coming chapters. And so the other thing that we're going to be considering in this is now we have some starting to be able to define how much scan time it takes to get all the data we need to reconstruct an image. And it's basically going to be the number of these phase encoding steps, so the number of different phase encoding gradient amplitudes that we're using, then times the TR, the repetition time. That's how long it's going to take us to fill in this full 2D data matrix that we're going to need to reconstruct our image. Okay, so this is a very important but very focused chapter here on building up these concepts of frequency encoding and phase encoding, and these are essential to understand this 2D-FT type of imaging. We talked briefly about back projection, although we're really focused on 2D-FT imaging methods, since it is by far the most common imaging method. And then we briefly discussed at the end there how we're going to be incrementing through our phase encoding steps and storing this data in our K-space matrix, which will then build on how we start to reconstruct images from that. Great, thank you for watching.